So this gives you an exhaustion, an increasing sequence, nested sequence that exhausts the rational numbers as q goes to infinity, the rational numbers between 0 and 1. And as all people who care about Diophantine approximation, one really only cares about rational numbers between 0. Everything else is just an integer translate. So it's a nice and amusing exercise to compute the cardinality of this set, how many elements are in this list. You sum up the Euler phi function, right? For any denominator little q, all the numbers relatively prime to it show up in this very sequence. And a nice exercise is to show that the cardinality of this, and here this double equal sign means that the ratio goes to 1 as q goes to infinity. You can say stronger things as well, but that's quite tricky. Is basically, it's 3 over pi squared q squared, and that 3 over pi squared is really a 1/2 times 1 over zeta of 2. And we'll see that in a minute. So one very basic notion of randomness is the notion of equidistribution. So if you have some sequence of lists, you might want to say that it spreads out completely evenly in the interval. So you have some sequence of lists of numbers and you want it to spread out completely evenly. That is, you want the proportion of elements of your list that land in any given interval to converge to the length of that interval. So they sort of mimic uniformly distributed random variables. That's certainly true in this case. I'm not going to prove it. Again, I'll leave that as an exercise. It's not a hard exercise. Okay? To compute, you can also tell your computer to do this, and your computer will tell you this as well very quickly. It's not a hard exercise to get your computer to tell you this, or some approximation. So in some very loose first-order sense, this list of numbers looks random. Now, I'm speaking to a room that's at least half full of ergodic theorists, so they're all shaking their heads right now, because many, many, many sequences satisfy this kind of equidistribution, but are not at all what you would call random. For instance, if you took a circle, or just the interval 0, 1, and moved by alpha mod 1, where alpha was some irrational number, that sequence of orbit points would also uniformly distribute. But nobody would ever call that actually random, right? Because that's very low complexity in the sense of dynamical systems. It's zero entropy, it's not mixing, it's not weak mixing, it doesn't have any of these properties that we associate with randomness. With the Ferry sequence, this is not coming from the orbit of a dynamical system, so what's the right question? I mean, if we can't, how do we talk about, say, mixing or weak mixing? We're going to talk about a different kind of notion of second-order randomness. The notion we're going to look at is the notion of what are called gap distributions. And this has been pioneered, I guess, I want to say Hermann Weyl looked at this for eigenvalue spaces of certain manifolds. But we're going to look at it just in this case of lists of numbers. So let me describe what happens in a truly random situation and the test we're going to run. So here's the baseline for our randomness test, which is the truly random situation. So we're going to generate a list that's as random as possible. We're going to sample from the unit interval 0, 1, IID uniform random variables. We're going to look at the first n sample points. And now we're not just going to look at where we've landed. We're going to think of the unit interval as a piece of string, and we're going to cut it up at the places where our points have landed. And once we've cut it up, we're going to look at the lengths of the pieces that remain. And these lengths are going to be what we're going to call the gaps, or the spacings. Namely, we're going to let x of 1 less than x of 2, can people see this, or should I zoom in further? People in the back, if this is okay? We let x of 1 less than x of 2 less than x of n be the order statistic. That is, we write these things in increasing order, the first n sample points. And we look at the differences. We look at the gap set, g of n, which is the difference, and then we normalize it by n, which is the number of points, because otherwise the lengths would all be getting very, very small. So we stretch out the interval by n, basically. And we ask, what's the proportion of them that are bigger than some fixed number t? So this is the proportion of gaps which are bigger than t. And it's not at all a trivial exercise in probability theory. The first time I gave this talk, I said it was an easy exercise in probability theory, then I tried to do it. And maybe I'm just not a very good probabilist, but it's not a trivial exercise, but it's an interesting one. You can compute the moments, and that's a way to get that this converges to e to the minus t. That is, the probability that the two guys are very far apart, that you have big gaps, is extremely small. The proportion of gaps that are big is extremely small. It's a very, very rare event. That is, one way to say this, a truly random sequence has an exponential gap distribution. Now let's look at the function e to the minus t. What are some things about it? This distribution has support at 0. In particular, you have lots and lots and lots of very small gaps. In fact, it's the mode of the distribution. It has exponential tail, as we saw. And in particular, that means all moments exist. So you can talk about the variance of the gap distribution and the 15th moment of the gap distribution. It's a very well-behaved distribution. So this is the question we're going to look at for the Fairy sequence. We're going to ask, what's the gap distribution? Cut up the unit interval at the Fairy points. Look at the lengths of the things that you get. Normalize appropriately and compute the gap distribution. Now, here's where I take a vote. Who thinks the gap distribution of the Fairy sequence will be exponential? Who thinks it won't? You're cheating. But you're also right. It won't. So the answer to this question, do Fairy sequences have exponential gap distribution, is no. And this is actually a beautiful theorem of a number theorist, R.R. Hall from York. And so before I state this theorem, let me set up exactly what I mean by normalize appropriately. So again, our Fairy sequence is gamma 0 is 0 over 1, less than gamma 1, all the way up to gamma n, and that n is n of q. And so the ith one I write is pi over qi. And then the gap, g of q, I don't normalize by the cardinality this time, but just by q squared. It's a little cleaner. So I normalize by q squared. It's basically the same thing as normalizing by the cardinality. Okay, so I look at the differences and I multiply by q squared. So by the way, that difference is just q squared over qi because the consecutive guys have the difference 1 over qi. So here's the theorem of Balls. Look at the proportion of Fairy fractions, of Fairy gaps in between A and B. A and B are just arbitrary positive real numbers. The limiting proportion is the area of this yellow region. The area of this yellow region, which is the area between the hyperbolas xy equals 1 over b and xy equals 1 over a, with the condition that the only area that we count lives in this blue triangle. The triangle which is I call the northeast corner of the unit square. So it's this hyperbolic strip, and it's twice the area because the area of this triangle is a half. Now, I went through Hall's proof, and I didn't understand the why of it. I couldn't check it line by line. But so what I'm going to do today is give you a proof that Yip-Hwa Chung and I came up with, that I do understand the why of, that uses horocycles. And I should mention that what Chung and I were doing was not trying to prove this theorem. What we were trying to do is we were trying to strengthen some shrinking target properties for the horocycle flow. So that's again something that almost mentioned. We were trying to prescribe some behavior for the horocycle flow on the modular surface. And completely by accident, we ended up giving a different proof of this theorem. So let's take a look at what Hall's distribution is. In this picture, which is taken from a paper by Boca and Zaharescu, the distribution is normalized here by n of q. So there's a factor of 3 over pi squared that's here. So what happens? There's absolutely no gaps at all until 3 over pi squared. Why is that? That's because this thing always at least 1. The QIs are less than or equal to Q. This thing is at least 1. So this, if you multiply by 3 over pi squared, it's always at least 3 over pi squared. There are no gaps which are smaller than 3 over pi squared. Then it jumps up and it has a nice differentiable shape. And then there's something that happens, funny happens here. That is 12 over pi squared. That 12 over pi squared corresponds to, well, this hyperbola hits at 1, and then it hits the bottom here at 4. xy equals 4, 1 over xy equals 4 is the point 1/2, 1/2. And so the shape of the region that you're delineating changes, which is that point of non-differential. So this is a nice picture. Now this, so fancy word, phase transition. Don't ask me why I called it that. Just seemed fancy. It has a quadratic tail, is maybe a more important thing. The probability of having a large gap, while still rare, decays quadratically. It's much less rare than for the truly random case. So in this sense, they don't really look random. They fail this already second order test of randomness. And in particular, there's no second moment. In fact, there's no moments beyond the first moment. It's a very poorly behaved distribution. It has a finite expectation, but it has infinite variance. It has infinite 1 plus epsilon moments. So it's it's what's called a heavy tail distribution. So I'm a geometer, not a number theorist. So if I want to understand the why of this problem, I need to translate it into geometry. And that's where we're going to get to the golden L eventually. The golden L will be a geometric generalization of this question. So the Ferry sequence consists of slopes of primitive integer vectors in this triangle, with vertices at 0, 0, and 0, q, and q's at 0, 0, q, 0, and q, q. Right? It's just slopes of vectors, integer vectors in this triangle. Right? There's nothing dramatic. Here's the sequence f of 4. And so if Ferry fractions are slopes, differences in Ferry fractions are differences in slopes. Nothing fancy. Now, we want to understand the differences in these slopes. So what we should, and remember, we also want to normalize appropriately. We want to multiply by q squared. So to multiply slopes by q squared, we're going to apply a linear map. We're going to renormalize by this linear map, 1 over q, 0, 0, q. That scales slopes of vectors by q squared, right? The rise, the x-coordinate gets shrunk by q. The run, the y-coordinate gets expanded by q. So the slope gets multiplied by q squared. And so we had our integer lattice, and now we've done a geodesic flow to our integer lattice. We've done this hyperbolic transformation, and we get this triangle now, a tall, thin triangle with vertices at 0, 0, 1, 0, and 1 comma q squared. What we've done is we've traded slopes less than or equal to 1 for horizontal components less than or equal to 1. So you can see the picture over here. So we've taken this triangle and we've made it into this very tall, very thin triangle. So this is for this lattice, which is the integer lattice, and then we've done this hyperbolic transformation. Why not ask this question for any lattice? You hand me a lattice in the plane. I look at the vectors which horizontal component at most 1, and I look at the differences in slopes. That's a general version of this question that one can ask. What's the distribution of differences of slopes? So that is, we're going to take L to be a unimodular lattice in the plane. That is, it's just two vectors, the integers span, and the vectors should span a parallelogram of area 1. In other words, we can write it, we have our two vectors, we make a parallelogram of area 1, their columns give me an element of SL2R. I can write any lattice as GZ2, where G is an SL2R, 2 by 2 integer determinant 1. Now what we do is we have this vertical strip, horizontal component length less than or equal to 1, and we look at the vectors that show up in this vertical strip. And we look at the slopes of these vectors. And we look at the differences in slopes of these vectors. So let's say S1 up to S2 up to S3, Sn is the sequence. The gap set is just the differences. Why don't I normalize? Because because these slopes are big numbers. I don't need to normalize. They're already big numbers. Right? Remember, I've already moved from my original lattice I've already multiplied by q squared. So now the question is, you give me a general lattice. Now this gives me some collection of points on the line. What's the limiting distribution? You put the probability distribution on this, the uniform probability distribution on this. What does that converge to as n goes to infinity? Does it converge to some nice probability distribution on this? And the answer is, perhaps unsurprisingly, this is a theorem of myself and Chung, but really Hall probably would have been able to prove it. If L does not have vertical vectors, if my original lattice does not have vertical vectors, then the probability measure supported on G of NL converges weak star to Hall's distribution. So again, that same area between two curves. We're going to prove this theorem and Hall's theorem using ergodic theory on the space of lattices. Okay? Ergodic theory of the horizontal flow on the space of lattices. So I need to introduce some of these characters. So the space of unimodular lattices, remember, each lattice we could write as GZ2, where G was in SL2. But the choice of G was obviously not unique. Even the original integer lattice Z2, it could be written as identity times Z2. But it could be written as any element of SL2Z times Z2 as well. So that choice is only well defined up to right multiplication by SL2Z. And that's unique. So we have this identification of the space of lattices with the coset space, or the homogeneous space, SL2R mod SL2Z. Via simply, the coset gets identified to GZ2. The horocycle flow is, for us, for our purposes, this lower triangular unipotent subgroup, 1, 0, minus S1. The reason we like this guy is that what it does is it shears vertically. So for instance, if you're looking at me and I'm the y-axis, so this will be the positive side for you guys, I think, yes? So what's going to do on the positive side, it's going to push things down, and on the negative side, it's going to push things up. So it's doing this shear, okay? But in particular, what this vertical shear does to slopes is it just subtracts S. If you have a vector, it just takes away S from the slope of that vector. Right? If I wanted to be fancy about this, I'd say as a projective transformation, it's acting by translation on the line. Right? It's just subtracting S. It fixes infinity and acts by minus S on the line. But in particular, if you subtract the same amount from everything, you preserve differences. You preserve differences in slopes. Why is it called horocycle flow? Well, many of you already know this, but for those who don't, its orbits on the upper half plane are horocycles. So we're not actually going to use that much. We're going to use just the Euclidean geometry. So what's our idea? Our idea is remember, we are interested in the differences in slopes. So I have my vertical strip, I have my vectors, and I want to understand what the differences are. I'm very bad at subtracting. So what I do is I run my flow until I'm allowed to subtract 0. I run my flow until I have a horizontal vector. Then the difference in slopes will just be the smallest positive slope of a vector in this strip. So since I'm bad at subtracting, I'm going to sample at times where I'm allowed just to subtract 0. That is, I sample the horocycle flow. I take a lattice L. I sample it at times when I have a horizontal length at most 1 vector. These times are just these slopes, Sn, and the differences are the return times. So that is, if I start with a lattice with a short horizontal vector, the difference that the next time I come back to the set is exactly that difference in slopes. So what we're actually doing in the language of dynamics is we're building a cross-section to the horocycle flow. We're building a Poincare section to the horocycle flow by sampling it along the set of times where the lattice has a short horizontal vector. So omega is a set of lattices with a short horizontal vector, and we want to understand how long it's going to take. If I have a lattice with a short horizontal vector, how long does it take me to come back to having a short horizontal vector? The first question is, how do we parameterize the set? So we want to know some function on this set. So I like coordinates. I want to describe a function in coordinates. So let me first give you coordinates for this. I claim that the set of lattices with a short horizontal vector can be parametrized by upper triangular matrices. By the upper triangular matrices x, y, 0, x inverse, with 0 less than xy less than or equal to 1, and x plus y strictly bigger than 1. Let's draw what that shape is. Here's 1, here's 1. Okay, so we're in this square somewhere, and we want x plus y bigger than or equal to 1. Hey, it's that triangle. It's that triangle that showed up in Ball's theorem. That's not a coincidence. How do we get this parameterization? Well, we know we have a short horizontal vector in our minds, right? So we might as well, if we have a short horizontal vector, we certainly have a short primitive horizontal vector, a short horizontal vector that's part of the basis. So let's call that vector, here's x0. Then we have some other vector which has to make a parallelogram with area 1 along with this vector. So that vector, maybe it's somewhere way over here. Maybe it's something like this. It's y x inverse. But what I'm allowed to do is I'm allowed to keep subtracting the vector x0 from it. And I can do that, and I keep subtracting until I end up in here. And that's what I call y x inverse. So this guy now has area 1. And I claim, so any issues with this? This is the heart of the construction. I have this vector and I just slide it along. I just keep subtracting x0. I'm allowed to do that. Lattice is a group, right? You can subtract. And now I claim that with this choice, this vector here is actually the vector with smallest slope in this strip. Because if I had something smaller, I'd get a co-area less than 1 is the problem. So if I call this lattice Lxy, the lattice up here, here is a crucial observation. Lxy comes back to this set at some point. It comes back, in fact, in exactly time 1 over xy. Because it comes back exactly when this guy becomes horizontal. And this guy becomes horizontal when exactly time equals to its slope. And where does it come back? That's also an interesting question. By the way, this is a picture of this set of lattices drawn in hyperbolic, the hyperbolic picture. It's just this, the guys above the line, y equals 1, with vertical tangent vectors. For any xy, the orbit returns. It comes back at exactly time 1 over xy, the slope of the vector y 1 over x. So there's that function. Remember, we were interested in hyperbolas intersecting this triangle. And the hyperbolas are exactly level sets of this function. And a direct calculation shows that where this thing returns is t of xy, which is y comma minus x plus floor 1 plus x over y times y. Now, it's a weird looking map. I'd like to just zoom in. What's this picture that I'm showing you here on the right? That picture is a picture of this triangle and then the function 1 over xy on this triangle. So this is a picture of SL2R mod SL2Z. Any point can be described as some point in the base, and then you go up a certain height. That, by the way, is nothing fancy. That's just row reduction. Because I'm saying everything can be written as an upper triangular matrix times a lower triangular matrix with 1s on the diagonal. But this is definitely one of the more interesting pictures of SL2R mod SL2Z I've seen. I wish I have a 3D printed model of this, but unfortunately I left it at home on my travels. So what's this map, by the way? Just to digress for a moment. What this map is it turns out that this map was discovered or invented, or however, depending on your philosophy you'd like to put it, by some number theorists. The number theorists were Boca, Covelli, and Zaharescu. And they were studying fairy fractions, problems related to Hall's theorem, and they wrote down this map. Now, they did not know about the Horocycle. So, in fact, when Chung and I had written down this map in this course of studying the shrinking target property, we were happy, but we thought, this is not that interesting, it's just a map. And then I went to a talk by Boca. Boca and Zaharescu are colleagues of mine at the University of Illinois. And I went to a talk by Boca, and he wrote down this map. And I got very excited, and I went to them after the talk, and I said, hey, we've been studying this map as well. And they asked, can you prove if it's ergodic? Can you prove that it's ergodic? Can you calculate its entropy? And of course, the answers to those questions, all the ergodic theorists in the room are now nodding, yes, it is ergodic. It's the first return map of an ergodic flow. Therefore, it itself is ergodic. What's its entropy? It's 0, because the entropy of the horocycle flow is 0. Incidentally, that's a little bit of an interesting story. For the horocycle flow on compact surfaces, the proof is completely written down. For non-compact, you have to assemble the proof from quite a few different pieces in the literature. I wasn't able to find it in one place. Horocycle flow being 0 entropy on a non-compact finite volume surface. Yeah, in Gurevich, or? Okay. So I'll get the reference from you then, because we reassembled a proof using some other pieces, some variational principles. So like I said, this map was introduced by Boca, Covelli, and Zaharescu, and hence we call it the BCZ map, in their study of fairy sequences. And you can see what the map does. The map is piecewise linear on all of these pieces. So it's linear on each one of these pieces. There's countably many pieces. The image of each piece is just flipping it over the line x equals y, but that's not what the map is doing. The map is ergodic. There's lots of open and interesting questions about this map, which would have some nice number theoretic applications. For instance, is the map mixing? Is it weak mixing? There is some progress towards weak mixing, but we don't know the answer to either question satisfactorily.
Can I interrupt you with
Yes.
a question back? So the triangle is the cross section, right?
Yes.
So, and the set it's the set length which have a horizontal vector, length 1 or less than equal?
Length less than or equal.
Okay.
So it's a two-dimensional. It's codimensional. If you specify it equals to 1, you get a one-dimensional set instead of a two-dimensional set.
Can you repeat again why it's a triangle?
Oh, it's a triangle because okay, so x. I agree that I can write anything with a short horizontal vector as like this. X 0, certainly, right? And then the second guy I can pick as y x inverse. Y I have some freedom. And I just picked y to be in this triangle. It doesn't have to be this triangle, it could be some other triangle. But this is a set of unique representatives. This is a choice. Yeah, absolutely, it is a choice. Not common. But it's a choice that makes it the same map here. Okay, so now we're actually ready to use the power of horocycle flow to compute our gap distributions. Now, by stating the problem in terms, by being able to translate the problem into a problem about horocycle flow, we have a lot of power at our disposal. So here's the principle. If you look at the lattice L of xy, the gap, the nth gap, is in between A and B. If and only if the return time function evaluated at the nth iterate of the return map is in between A and B. The if and only if is because those two quantities in the middle are equal, right? It's this, I could have stated it much simply. The return time of t to the nxy is precisely this gap. But in particular, what that means is the proportion of gaps in between A and B is exactly a Birkhoff sum. It's a Birkhoff sum of this, it's the Birkhoff sum of the indicator function of this set. Right, the area between these two hyperbolae. So in particular, I've turned this gap distribution question into an equidistribution question, into an ergodic theory question about the ergodic theory of this map. That's the power of this. And now, every non-periodic orbit of the horocycle flow on SL2 or mod SL2Z equidistributes with respect to our measure. That's a theorem of Dany's. And that gives us our theorem for generic lattices, because if you take a lattice that doesn't have a vertical vector, it's not periodic under this horocycle. And therefore it equidistributes, and therefore it equidistributes on the return, on the section as well. But now you might say, what about Hall's theorem? Those emphatically have vertical vectors, and emphatically the integer lattice is periodic under the horocycle flow, right? You do the horocycle flow for time 1, and you snap back onto the integer lattice. But that's also fine, because we're not really interested in the integer lattice, we're interested in this lattice. And this lattice, I claim, and this is a fun check, HQ squared is actually just equal to itself. It has a period Q squared under the horocycle flow, which corresponds to the fact that, in fact, T to the n of Q of the point 1 over Q1 is 1 over Q1. Now, you might say you have 1 over Q0 here, but of course it's the same thing as 1 over Q. You just add Q times this thing. And so now you use the equidistribution of long periodic orbits, which Sarnak gave a proof of, but you can also give a proof of using mixing of the geodesic flow, for instance. It gives us Hall's theorem, and in fact, many, many other results. So Boca and Zaharescu and Augustine and Kobeli and a few other co-authors had a cottage industry of proving various theorems about statistics of these Ferri fractions, moments, various other indices, and so on. Every single one of those theorems in the end is a consequence of this second equidistribution. So our paper unifies and explains about 10 or 12 theorems of theirs, which we're quite happy with. It gives a couple of new results as well. It also gives a proof of a result of Hall and Tenenbaum on statistics. So now I want to talk about the title of this talk, which was the Golden Elf. We spent a lot of time on the Ferri fractions, but I needed to do that to set up why this problem really is interesting. So now I want to use the word exotic gap distribution. And this comes from a beautiful, beautiful paper by Elkies and McMullen, who studied the gaps between square root of n model. They looked at the sequence of square roots of integers, the fractional part, and they looked at the gaps. It was noticed by Bozer-Nietzsche in some computer experiments that these gaps behaved very strangely. Gaps for any other power that was not a half, n to the alpha model, satisfied exponential distribution, at least experimentally. I don't know a proof of that, but experimentally. But experimentally, n to the square root of n mod 1 didn't. And Elkies and McMullen used, again, ergodic theory of the horocycle flow, this time on the space of affine lattices, to compute explicitly what the distribution was. And they have this beautiful quote, classic McMullen: the uniform distribution of lattices explains the exotic distribution of gaps. And of course, the same principle is true for Hall's distribution. Markov and Strombergson then studied general affine lattices in higher dimensions and found analogous results. In particular, in 2 dimensions, they found that if you study a lattice translated by a vector which is irrational with respect to that lattice, the gap distribution for slopes or for directions is the same as for square root of n mod 1. And the only explanation of that I know comes from homogeneous dynamics. I don't know of an intrinsic explanation for that, why that should be. So motivated by these results and by results of Veach and of Vorobets, John Chaika and Samuel Lelievre and I, in 2 separate projects, decided to study what was called the gap distribution for saddle connection directions on translation surfaces. So this is the world that I come from, which is the world of what are called translation surfaces, which you'll hear more about. Barak Weiss will speak more about them tomorrow. So I want to give a very, very brief introduction. How much time do I have left? I want to give a very brief introduction and state the golden L theorem. So I claim that all this time that we've been working with Ferri fractions, what we've really been working with is torque. Because if you take a lattice and you quotient out the complex plane by the lattice, you get a torus. And the lattice points are just closed geodesics in the flat metric that you get on this torus. We get closed geodesics through 0. So in particular, here's a picture. And notice when we're quotienting out, we're really quotienting out by the group acting on itself by translation, by this lattice lambda acting on C by translation. So what we're doing is we're taking the square and we're gluing the left to the right by translation, the top to the bottom by the translation to get this. Here's a question. Can we do this in some sort of reasonable way to make a higher genus surface? Can we build a higher genus surface out of taking some shape in the plane and gluing things up by a translation? And the answer is yes. Here are some genus 2 translation surfaces. Here is a picture taken from Antoine Zorich's beautiful survey, which I highly recommend if you want to learn about the subject. Take a regular octagon and glue parallel sides by translation. So first, you have this, you do it with the square, and you get this torus with a square-shaped hole whose opposite sides are identified. And you build another handle. But you should all notice there's something funny happening. Look, we have this nice graph paper here, and the graph paper was still doing fine, except now we have some weird angle going on here, and what's going on here is we have way too many pieces of graph paper meeting. What's going on here is we have a total angle of 6 pi at this point. Everywhere else is a perfectly reasonable point. Here we have a total angle of 6 pi. Similarly, so genus 2, one singular point, angle 1080 degrees. More generally, a regular 4G gon gives you a genus G surface with one singular point of angle 4G minus 2 times pi. Similarly, if you do an L and the sides here are identified by color, then again, well, if you think about it for a second topologically, the way I've drawn it with vertices, this is just an octagon. So you get the same. There's 8 sides, and they're paired. If you do a decagon, you get a genus 2 surface with 2 singular points, each with angle 720 degrees. You get each with angle 4 pi. Now, the way to parametrize this data, of course you could say polygon with translations and so on, but the correct way to parametrize this data is what are we getting? We have something sitting in the complex plane and we're gluing everything up by translations. Translations are holomorphic, so we get a Riemann surface certainly on the identified object. Translations also preserve dz, right? Even your calculus students can tell you d of z plus c is d of z. So what you get is you get a Riemann surface together with a holomorphic one form. That's what a translation surface is. And what we're interested in, remember we were interested in these closed geodesics on the torus. These are things that connect 0 to itself. A saddle connection is a geodesic in the flat metric which connects 2 singular points. Remember we had these singular points. What those singular points are in this complex analytic data are zeros of the holomorphic one. So a saddle connection is just a straight line connecting 2 zeros. So for example, for example, these are some saddle connections, these dashed lines. So here's the saddle connection. Particular attention to the purple guy. It goes here, comes back here, and finishes up here. And now you can see to each saddle connection I can associate a vector, which is just how far I've gone horizontally and how far I've gone vertically. This is called the holonomy of the saddle connection. So in complex analytic language, what I'm doing is I integrate the one form along the saddle connection. And I get a complex number, I get a vector. The collection of these vectors is a discrete subset of the plane. That's a theorem. Then a deeper theorem is that that has quadratic asymptotics. The number of them of length less than or equal to r is like r squared times some constant. Mazur, Veach, Eskin, Mazur all make serious contributions. Mazur proved that you're caught between two constants. Veach and Eskin Mazur proved that in many cases you're actually on the nose quadratic. And in particular, we don't know of any surface which is not, and I would bet against the existence of such. And what Veach showed is that for particular, very highly symmetric kinds of surfaces, in particular, for example, the torus, the directions that these guys show up in equidistribute on the circle. Vorovec showed this in more generality. He showed this for surfaces which are very non-symmetric or are sort of more generic. And so now the natural question for us comes, what's the gap distribution? So they look random according to this first thing. These saddle connections are showing up in random directions. Are they showing up truly random? So with John Chaika, we showed that the distribution exists for a generic surface. That for a generic surface, it has support at 0. And I'm not going to define what generic surface is. I'll leave that for Baroda for tomorrow. The distribution, again, is not exponential. Like the torus, again, it has quadratic tail. And there's a little bit of a lie in here. The lack of support at 0 characterizes highly symmetric surfaces. This is actually basically goes through some work of Barak and John Smiley's. However, we couldn't explicitly compute the distribution for any particular example, which was disappointing, other than the torus. So the torus we knew. So here's one where we now can do. This is called the golden L. The golden L, because its long sides are length golden ratio. Now, what do I mean when I say it's a highly symmetric surface? I claim this is a very highly symmetric surface. There's an SL2R action on the space of translation surface. It's very simple. You give me your polygon, just move it linearly by your matrix. SL2R acts linearly on the plane. So SL2R acts on this. It turns out that this particular guy has an enormous stabilizer under SL2R. It has the 2, 5, infinity Hecke triangle group under this, the stabilizer under the SL2R action. Just like the torus had the 2, 3, infinity Hecke triangle group as its stabilizer. So in some sense, it's the next simplest example. And now what we do, so this project started, there's the golden L, when Samuel Lelièvre sent me the following picture, which let me zoom in on. So he sent me this picture, and he said, can you prove a theorem about it? Literally, he said, can you prove a theorem about it? And the answer, of course, is yes, of course we can prove a theorem about it. And so these are what this picture is this is the set of saddle connections for the golden. If you don't like translation surfaces, what this is this is an orbit of the 2, 5 infinity group acting linearly on the plane. It's the orbit of the point 1, 0, acting linearly. To get 1, 0 and golden ratios. It's the beauty of 2 points. So what we did is we computed explicitly the gap distribution. And the reason I spent so much time on the torus case is because we did exactly the same thing. We said, let's build a cross-section. Let's look at the space of golden L's, which is SL2R mod the 2, 5 infinity Hecke triangle. Inside of it, let's build a cross-section, which are the golden L's, which have a horizontal length less than or equal to 1 saddle connection. Let's compute the return time function. Let's compute the return map. And here's what we got. Here is what we guessed what it would be, theoretically, using this strategy. We didn't believe this. We said it has too many points of non-differentiability. It's too irregular. So we did what we should have done in the beginning, given that we had the data. We computed the empirical distribution using the data. That's the empirical, that's the theoretical. We were right. We were right. And, oops, sorry. Let's just go back for a second. And that's what the cross-section is parametrized by the set. And these are various pieces of the return. So let me just give a few suggestions for further reading. If this talk doesn't motivate you to do anything else, please let it motivate you to read this paper by Elkis and McWall. It's absolutely gorgeous. And also this Markov and Strombergson, it's a little more challenging, but it's another beautiful paper. And then there's a few papers that this work is based on. The work with Chaika and Laleevra is still in progress. We're still writing it up. It should be close to it. But with that, let me stop and say thank you.